Good day everyone. We're here to present our thesis about the optimization of printing parameters for 3D printed conductive electrodes in vermiculture-based microbial fuel cell. One promising technology in the field of bioenergy is vermiculture-based microbial fuel cells, or VMFCs. This system generates bioelectricity by harnessing the natural processes of microorganisms and worms. The potential of VMFCs lies in their ability to convert organic waste into energy, making them an attractive option for sustainable power generation. However, the efficiency of VMFCs heavily depends on the performance of the electrode, which are critical components of the system. The electrodes facilitate the transfer of electrons, which is essential for generating electricity. Poor electrode performance can significantly reduce the overall efficiency of the VMFC. 3D printing has emerged as a versatile method for producing custom electrode design tailored to the specific needs of VMFCs. This technology allows for precise control over the design and manufacturing process, enabling the creation of electrodes that can potentially enhance the efficiency and effectiveness of these systems. However, the success of 3D printed electrodes in VMFCs depends on optimizing the printing parameters. This brings us to the core issue that this thesis seeks to address. There is a limited research on how the various 3D printing parameters affect the conductive properties and overall functionality of the electrode. Without a clear understanding of these printing parameter relationships, optimizing the electrode manufacturing process to enhance VMFC performance remains a significant challenge. Given the challenges outlined in the problem statement, it becomes crucial to define a clear objective for this research. For this study, it aims to maximize the surface area ratio of 3D printed electrodes by evaluating the effects of different printing parameters on their electrical properties. Understanding the objective of this research naturally leads to consider its broader impact. The significance of this study lies in its potential to contribute to global efforts to reduce greenhouse gas emissions and environmental pollutants. By advancing the efficiency of VMFCs, this research supports the Sustainable Development Goals 7 and 13, which focus on affordable and clean energy and climate action respectively. While this research aims to optimize electrodes, there are certain boundaries and constraints that must be acknowledged to understand the context and applicability of the findings. The first is this study optimizes conductive PLA electrodes and does not explore alternative materials or long-term electrode stability. This study also primarily focuses on short-term experiments to assess electrode performance. It also does not address the impact of large-scale implementations, economic feasibility, or geographical variation on performance. Let's delve into the methodology that guides this research. We'll start by discussing the conductive electrode model. The electrode design was adapted from the Matulak and Tandayos model. The cathode and anode were 3D printed using conductive PLA filament, while the separator are printed using PLA filament. These electrodes were printed using Creality Ender Pro 3. Next, we will discuss the printing parameters. Four specific parameters were adjusted using Ultimaker Cura: printing speed, printing temperature, resolution, and infill density. This approach allowed us to assess the impact of printing speed on print quality, structural integrity, and conductivity. We varied the printing temperature to observe its effects on layer adhesion, material flow, and overall conductivity. Resolution was adjusted to evaluate its role in achieving fine details and smooth surfaces. Finally, we manipulated the infill density to explore its impact on structural strength and overall conductivity. For the optimization strategy, a 2 to 4 factorial design was employed. We established low and high conditions for each parameter. For the low conditions, we use a printing speed of 20 mm per second, a temperature of 190 degrees Celsius, a resolution of 0.2 mm, and an infill density of 50%. For the high conditions, the parameter was set to a printing speed of 60 mm per second, a temperature of 210 degrees Celsius, a resolution of 0.1 mm, and an infill density of 100%. The table here illustrates the distinct combinations of these four parameters, ensuring for each combination is unique and non-repetitive. The vermiculture setup comprised the watered sludge sourced from the GMA Water District Septage Treatment Plant, African nightcrawlers from Valenzuela worm farm, and soil collected from Pampanga. Each setup utilized the watered sludge, which includes both organic and inorganic solids. The total volume for each setup was 50 liters, consisting of 13.87 kilograms of the watered sludge and 10 kilograms of soil. Three separate setups were prepared, each serving as an individual trial with 16 electrodes per trial. Prior to introducing the worms, each setup underwent a 2-week acclimatization period. Following this period, 400 grams of African nightcrawlers were introduced into each setup to initiate the vermiculture process. Data acquisition and evaluation began with measuring the electrical resistance of the printed electrodes to assess their conductivity. The resistance was recorded in kiloohms as illustrated in the accompanying pictures. The 3D printed anode and cathode were measured using alligator clips attached to a multimeter. This method allowed for accurate readings of the electrode's conductive properties, providing essential data for evaluating their performance. Next, we evaluated the water retention capacity of the electrodes by measuring the time required for half of the water volume to leak or evaporate. This duration, recorded in minutes, provided insights into the electrode's ability to retain moisture, which is crucial for sustaining microbial activity in the microbial fuel cell. Throughout the 24-day operation period, The electrodes were installed in the vermiculture setup and regularly watered to maintain adequate moisture levels and ensure active microbial growth. Voltage and current data were continuously monitored using multimeter and alligator clips to track the system's performance. Lastly, 3 anode samples were submitted to NASA labs for scanning electron microscopy, imaging, and analysis to gain detailed information about the electrode outer surfaces. To assess the significance of the main effects and interaction between the various factors, we employed analysis of variance or ANOVA. This method allowed us to analyze the impact of 4 key factors: printing speed, printing temperature, resolution, and infill density, on our response variables, which include current, resistance, voltage, and water retention. The ANOVA approach helped us determine how each factor individually affected the performance metrics, as well as how combinations of these factors interacted to influence the outcome. For the statistical analysis, we use Excel to perform one-way ANOVA, and Origin Pro was utilized to create 2 y-axis graphs, which provided a clear visualization of the results. Having covered the methodology and data acquisition processes, let's now turn our attention to the results and discussion. To begin with, the total printing time for one trial amounted to 75 hours and 21 minutes. Considering that the study comprises 3 trials, the cumulative printing time reached 226 hours. We can now examine the outcomes in detail. Here are the pictures taken after the printing process of the anode and cathode for trial 1, followed by the images captured after the experiment was shown for trial 2. Additionally, you will see a side-by-side comparison of the anode or cathode before and after the experiment to highlight the changes observed. During the printing process, it was observed that the conductive filament frequently clogged the nozzle, resulting in a rough outer surface on some of the printed electrodes. This variation in texture is shown in the pictures, specifically anodes 1 and 2, along with cathodes 9 and 10 exhibited smooth surfaces, whereas anodes 3 and 4 and cathodes 11 and 12 had rougher surfaces. This difference in surface texture had a notable impact on the resistance measurements. The smooth surface anodes 1 and 2 demonstrated higher resistance value of 178.4 kiloohms and 884 kiloohms, respectively. In contrast, the rough surface anodes 3 and 4 had lower resistance values of 31.15 kiloohms and 44.4. Similarly, among the cathodes, the smooth surface cathodes 9 and 10 recorded resistance values of 313.9 kiloohms and 679 kiloohms, while the rough surface cathodes 11 and 12 showed lower resistance value of 629 kiloohms and 166.1 kiloohms. As shown in the picture, the rough surfaces of the electrodes allowed the alligator clips to grip more securely, resulting in more accurate and stable resistant readings. In contrast, the smoother surfaces caused the clips to slip, leading to rapid fluctuations on the multimeter and making it challenging to obtain consistent resistance values. This variability in surface texture and its impact on resistance underscores the importance of maintaining a consistent electrode surface quality to ensure reliable measurements. Additionally, during the 24-day operation period of the VMFC setup, there were instances where some worms either escaped or died. This issue may have been influenced by the quality of the dewatered sludge used in the setup. Inemanova et al. Indicates that earthworms can thrive in dewatered sludge under specific conditions, suggesting that a preliminary test of the sludge could help prevent such issues. However, due to practical limitations, the exact number of escaped or deceased worms were not recorded. This omission may have affected the system's microbial activity and overall performance. Despite this limitation, we will continue to rely on the statistical analysis to interpret the results and assess the impact of these variables on the overall performance of the VMFC setup.
So we are now done to a comparative analysis. So after 28 days of accumulating data regarding voltage, current, anode, and cathode resistance, we developed graphs to fully understand the relationship prior to identify the best conditions of parameter for a certain response variable. So in the graph, run 6 achieves the highest voltage with a high printing speed, low temperature, and high resolution, and low infill density. Voltage is generally higher with a faster printing speed and higher resolution, while infill density varies. However, run 6 shows high variability as it indicated by the white error bar. So for our water retention, run 13 stand out with a low printing speed, low temperature, high resolution, and high infill density. Water retention is strongly influenced by the higher infill density and resolution with the minimal variability despite slightly inconsistent with data. So lastly, run 16 produced the highest current with high printing speed, high temperature, and high resolution, and high infill density. High currents correlate with the high speed and temperature with the error bar consistently low at 0.3 to 0.4, indicating a stable data. Since run 6 has the highest voltage, we compare its performance on anode and cathodes. For the anode, variability is high in run 1, 2, and 13, showing significant fluctuations. Run 2 exhibit the highest anode resistance with high printing speed, low temperature, low resolution, and low infill density. Anode resistance tends to be high with varying parameter but consistently low temperature and resolutions. On the cathodes, variability is generally consistent except for an upward spike in run 6, which also produced the highest current under high speed, low temperature, high resolution, and low infill density. High cathode resistance occur under diverse parameters but consistently low temperature. So in the graph, run 16 achieves the highest current with high printing speed and temperature, along with varying infill density and resolution. High cathode resistance is mostly observed at low temperature with varying speed, infill densities, and resolution. Similarly, high anode resistance occur at low temperature and resolutions with varying speed and infill densities. So in this bar graph show consistent data for current, with run 16 producing the highest current and run 13 the highest water retentions. High resolution is critical for both enhancing electrical and physical properties, while high infill density improves conductivity and moisture retentions. So lastly, low printing temperature consistently increase anode and cathode resistance but has variable effect on water retentions. So low resolution is linked to higher resistance, while higher resolutions improve water retentions. So low infill density arises resistance, whereas high infill density enhances water retentions. So the effect of printing speed varies across matrix, suggesting it plays secondary rules compared to the other parameters. So we are now down to scanning electron microscopy, SEM imaging analysis. So the selected samples here were based on their significant connections between the high and low voltage, current, water retentions, and resistance values. So these selected samples offer insight on the structural integrity as well as the influence of soil, microbial activities, and the water sludge affect the performance of the anode, since anodes are the only components that expose to internal environment. So we choose anode 6 in trial 2 due to its surface characteristic as it's seen from a macroscopic perspective. It has a smooth surface with line patterns and particle in gaps. So the surface shows varied particle size and shape, including a large central agglomerate surrounded by smaller particles as it's seen in figures A, B, and C. So the bright agglomerate suggests heavier elements like soil minerals or metal oxides accumulated over 38 days of burial. So the whitest particles here likely indicate mineral deposits from the water sludge or carbonate precipitated by microbial activity. So we choose anode 2 in trial 1 for its distinct surface feature. It has a smooth surface with the line patterns, but this contains larger and more accumulated particles compared to anode 6. So figure C reveals particle alignment within crack, indicating advanced fragmentations. Whiter areas suggest rust, while parallel lines hit at erosions, reducing surface area and structural integrity. Significant degradations in their current conductions and electrochemical stability, risking potential future failure. So burying the anode in the soil and sludge contribute to this, embedding soil's particles into the surface and promoting agglomerate formulations. So we choose anode 13 in trial 3 for its intriguing surface feature. So for figure C shows highly worn strip or rounded designs, indicating significant physical and chemical stress. So dense agglomerates and embedded rock suggest material degradations due to interactions between the anode and foreign particles. Figure D highlights deteriorations caused by mechanical wear, chemical corrosions, and moisture infiltrations, further weakening the anode's structure. So the overall conditions reflect harsh environmental effect, resulting to its visible wear and damage. So we are now down to ANOVA results on response variables. So the ANOVA result shows that the printing parameter, which is speed, temperature, resolution, and infill density, had no statistically significant impact on water retentions, voltage, current, or electrode resistance. So the F values ranges from 0.68 to 1.66 with P values between 0.11 and 0.79, all above the 0.05 significant threshold. So this indicates that the variations in these parameters did not cause substantial differences in the response variable for either cathode and anode. So a detailed analysis of printing parameters reveal a minimal impact on the response variables. So infill density, resolution, speed, and temperature show also a low F values and high P value, indicating no significant effect on the water retentions, voltage, or currents. So while cathode and anode resistance shows slight differences, these were not also statistically significant. So overall, the printing parameter had no negligible influence on the performance metric in this study. So after all said and done, we conclude that high printing speed and resolution generally improve voltage and current, as it's seen in run 6 and 13. Low printing speed and high resolutions are more effective for water retention, as it shows in run 5. So for example, run 6 had a strong combinations of high speed, low temperature, high resolution, and low infill density. Run 2 achieved high current but faced increased anode resistance, limiting its performance. Similarly, run 13 prioritized water retentions but experienced lower voltage and currents, highlighting the difficulty in balancing performance feature. So anode 6 with a smooth surface and minimal agglomeration shows good electrical performance. In contrast, the surface segregations and contaminants on anode 2 lead to a high resistance and reduced efficiency. Anode 13 with severe wear and dense agglomerates achieve high water retentions but at the cost of lower electrical output. So the ANOVA result shows no statistically difference in the response variable or printing parameters. So therefore, optimizing electrodes performance will require adjusting printing parameters based on a specific response variable target in a future studies.
To improve the overall effectiveness of the vermiculture-based microbial fuel cell, it is recommended to select a filament that minimizes clogging and exhibit low electrical resistance to enhance both the printing process and electrode performance. Additionally, a thorough evaluation of the water sludge, organic and inorganic components is essential to assess its suitability for supporting vermiculture effectively. Furthermore, conducting elemental analysis through scanning electron microscopy can provide detailed insights into the material's composition, particularly in the anode areas, which is crucial for understanding how these components influence electrode functionality. In addition, it is advisable to pursue further optimization of 3D printing parameters by experimenting with different settings. This will help refine the quality and performance of the electrodes, leading to more precise and efficient production and ultimately improve performance of the microbial fuel cell.